few basic definition. Otherwise, okay. So basically, I am recalling what is called proof field ring. Then I will start formally. One. Let G be a non-empty set. G is called a. So what is the definition of group? What is the definition of group?
If star is a binary operation, G is close to the star, or star is a 31G, there is an identity on in G for star, and for every element in G, there exists an inverse.
Is the identity unique?
Yes.
Okay. The map. No. Set. And we have no. Let me write it that fashion. And we have binary operation. And we have a binary operation. We say G comma dot the group if A compose B compose C equal to A compose B compose C for all A B C and G B definition. Okay. One, two. There is E belongs to G such that E into A equal to A into E equal to A. For each A belongs to G, there is E belongs to G such that AB equal to BA equal to E. In addition, if AB equal to BA for all A B belongs to G, we say G is abelian. Okay, G is called abelian. Two, let R plus be an abelian group. Suppose we have another binary operation multiplication such that 1 what r dot is a semigroup. 2. Addition is distributive over multiplication. Okay, a into b plus c, ab plus ac for all a b c belongs to r. Same holds for from the right. আমার ইন্টারনেট কানেকশনের সমস্যা আছে, আমি খেয়াল করিনি, বেরিয়ে গেছিলাম। কতটা অবধি দেখতে পেয়েছো? হ্যালো,
B plus
কথাটা দেখো। রিং এর ডেফিনেশন কি? We have an abelian group, then we have some extra structure, multiplication, that satisfies some condition. So then we say that okay, this is a ring. So everybody know what is the definition of monoid semigroup? Monoid and semigroup, I have written terms here. Yes, one is monoid and another one is semigroup. What do you mean by monoid and semigroup?
semigroup মানে তো মানে a set which will follow the associative law, আর monoid মানে associative law hold করবে আর প্লাস একটা ইউনিক আইডেন্টিটি থাকবে।
No. Okay, semigroup means yes, closureness and associativity, and monoid means identity. Yes. So a ring may not have identity, so a priori it is a semigroup. Just if we put the identity, then it becomes a monoid. So so if there is some 1r such that a into 1 times r blah 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 happens, then it is a monoid. This is a multiplicative identity and it becomes a monoid. Okay, convention.
একটু উপরে তুলবে, just slightly.
We mostly work with commutative rings with unity. You mostly work with so you haven't see the definition of ring yet, right? You don't know what is ring?
না মানে properly না।
Okay, so you have seen the definition for the first time. Okay, so you know what is something called group, so I am not going to give any example of group, but okay, so since you have seen the definition of ring for the first time, I am going to give the definition, some few examples. So okay, so okay, it is okay. Is it okay? Few examples. Let R equal to Z. Mm, okay. So you said that you have seen the construction of Z. So does it a ring? Is Z a ring? Is there any multiplication on Z?
Yeah.
Yeah, what is the multiplication? What is the multiplication? You know the meaning of this symbol? Colon equal to, it's called colon, right? Okay. You know the meaning of this symbol?
I have defined by.
Yes. So what is the multiplication on Z? Now the question is, what do you mean by AB? Now the question is, what do you mean by AB? So you can't directly answer what do you mean by AB. You have to go to the natural number first, then define the multiplication there. Then you have to extend it in to the all Z. Then to Q, then to R. So if someone say what do you mean by the multiplication of two real number, you can't say directly. You have to say it for natural number, then integer, then uh, uh, okay, then for rational, then for real. It is not so easy. I I I I may ask, what do you mean by AB? This number. What is that? What is the relation with A and B? Okay, fine AB. All this comes from piano section. Piano section means construction of natural number. There is 1 belongs to R such that 1 equal to A1 equal to A and AB equal to BA for all AB belongs to Z. So Z is our first example of a commutative ring. This implies Z is a commutative ring with unity. A very good example. Okay. So any other example? The first one. Any other example? revisit an axiom, but to see that QRC are also rings, but we have something more here. Okay. Example 3. Everybody knows what we mean by matrix. What is the definition of matrix? What is the definition of matrix? Come on. There's a whole chapter of matrix in class 12. But not in that fashion. Late are waiting. Over R is also a ring with unity. Is it commutative? Is it commutative? Is it commutative? So, okay, I need to introduce something more. Something called polynomial ring. Okay. Mm, that are very commutative. Okay. Definition. Bad. Example 1. 3. Let R plus dot be a ring. Be a commutative ring with unity. R is said to be filled if for every non-zero R belongs to R, there is S belongs to R such that R is equal to 1. Every non-zero R has a multiplicative inverse. Then we called R to be a field. Okay. Example Next page. What is the example of field? Yes, what is the example of field?
Real numbers.
Okay, can you prove it? The question is, can you prove it? It is not so easy to prove. First of all, you need to go back to the definition of Dedica, the construction of real number in Dedica cart or in Cauchy construction. Then what do you mean by real number? Real number, if you see the Dedica cart construction, you see that there is something called cart. Cart are the subset of rational number. So every real number corresponds to a subset of rational number. If we see every real number as a subset of as a certain subsets of real number, rational number, we call them cart. And if we have a two non-zero real number that corresponds to some carts, then we need to show that if we multiply these two carts, then we get the identity cart. Otherwise, you can't prove. What do you mean by okay? What do you mean by root 2? What do you mean by pi? We don't know. What do you mean by pi? What do you mean by root 2? Either you go from the cut or you go from the Cauchy construction. Cauchy construction is the same thing also. So proving R is a field is a bit tedious job. What about proving C is a field? What about proving C is a field? Example. C. What is the proof that C is a field? Okay. C R R C. Okay. C as a set C is NOTH nothing but up to addition and multiplication on C as follows. A comma B, C comma D is defined to be A plus C comma B plus D, and A comma B dot C comma D is defined to be what is A plus ID C plus ID AC minus BD comma AC minus BD A plus IB A plus IB C plus ID AC minus BD plus I2 AD plus BC. check that R2 plus this multiplication is a field which is known as C. All these are exercises. These are exercises. Okay. So, okay. Again definition. Let R bearing a set is called ideal of R if A belongs to I okay. So is the definition clear? What do you mean by ideal of a ring? Is it okay?
মানে for all A belongs to I, there will exist some
Yeah.
R in R.
For all A comma B. No. For all A and for all R. This holds.
আচ্ছা, okay.
If you take any two elements from I and add them, it is in I. If you take any element from A and any element from the ring, if you scale them, then it is inside I. That's the basic thing. This is an ideal. What do you mean by ideal? So basically, ideal is a subgroup. First of all, ideal is a subgroup of R with some additional properties. Okay. We need some basic preliminaries to start the subject linear algebra. We need, not now, but we need something called polynomial ring, division algorithm, and this concept of ideal when we are doing other things. Okay. Example, let R equal to Z. Then R equal to Z and I equal to NZ. You know what do you mean by NZ? Check that I is an ideal of R. Okay. We know what do so what is NZ? NZ is the n times A belongs to Z. At 2 let R be any ring, then is the ideal. Okay. Okay. So is the third one clear? I am going to prove it. Is the third one clear? Since you are seeing the ring theory for first time, I am not going to say that okay, prove that any ideal of a field is either zero or the whole. Okay, I will prove that for you. Is the statement clear? Example 3. Is it clear?
Yeah, that's it means clear.
Okay, so basically, okay, so by 2, 0 and R are the ideals of R. But but it said something more. If R has any other ideal, then this is of the form either 0 or R. Okay. Okay. Let I subset of R be an ideal and I not equal to 0, I not equal to R. Okay. So I have taken an ideal which is not the zero ideal, is not the whole ring, and I want to show some contradiction. This will prove that okay, so these are the only ideals of field. Since it is a non-zero ideal, so uh, I can find a non-zero element inside the ideal I. Okay. I can find, right? It is a non-zero ideal.
Yeah.
Okay. So now go back to the definition of field, where it is. The definition of field is saying that R is said to be a field if in every non-zero R there is a S such that R is equal to 1. Every non-zero element has an inverse. Okay. By definition of field, there is Y belongs to R such that xy equal to 1, right? By condition 2 of ideal, 1 is in I, right?
Yeah.
X is from I and Y is from
Oh, it's from R.
R, so
So
multiplied
it's
by, yeah. So now 1 is in I. Take A from R, be any I am taking any arbitrary element, again by condition 2 of ideal. What I can say? By condition 2 of ideal, what I can say?
that A belongs to I.
Yes, that's the most crucial part. And it is true for any ideal. If ideal contains the identity element, then it contains the whole ring. Ideal A belongs to I. This implies R is contained in I. But I is contained in R. This implies R equal to I. But I not equal to R is a, but we take I not equal to R. So this is the contradiction. So therefore there is no such ideal exist other than 0 and R. Okay. Okay. Is the proof okay?
Yeah.
Yes.
এই জায়গাটা একটু রেখো, এক সেকেন্ড, একটা জিনিস লেখা বাকি আছে।
কোনখানটা?
ওই যে take A belongs to R,
Okay, you are writing the notes.
পাঠিয়ে দেবে?
Yes.
ওকে ওকে।
Okay. So is the proof clear for to everyone? If you have any question, please ask. Okay. A property of field. Let R be a field and A comma B belongs to R. Then AB equal to 0 implies either A equal to 0 or B equal to 0. We are using this for real number from the very young age, that if any two element we have any two real numbers multiply it is 0, then they are either one of them is 0. So what is the proof? So in particularly R is the set of real number is a field, so this also holds for real number. We are using it, but what is the proof? That if I have two elements from field, I have two elements of field. If I multiply and then it becomes 0, then either one of them has to be 0. What is the proof? Anyone?
If AB belongs to field, then and AB equals 0, then B inverse exists in A. So,
B may be 0.
B
AB,
inverse exists in A.
sorry,
B inverse exists in A.
B may be the 0 element.
No, no, B inverse exists in A.
No, in a field, we say any non-zero element. We don't define a inverse of a 0 element. What do you mean by something like this? Your approach is correct, but what do you mean by 1 by 0?
No, B is non-zero element.
No, you haven't said that. You have to take one of them to be non-zero. Your approach is correct, but you have to say that. Okay. Suppose if one of them is 0, then we are done. If A is non-zero, then A inverse is in R. So AB equal to 0 implies A inverse AB equal to also 0. A inverse A B equal to 0. This implies B equal to 0. Done. So one of them has to be 0. Both of them may be 0. If both of them not 0, then one of them has to be 0. If both of them. If not, then we have this. Okay. 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 Okay, I will define polynomial ring later. You need that. I will define polynomial ring later. But there are, so I left few exercises like checking, well, checking that nz is an ideal of z. Then q or c are the example of field. Another one. Okay, another one is MNR a field. Exercises. Is MNR a field? This R is real number. Is MNR a field? Okay. 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 So, okay. So, okay, the name of the subject is linear algebra. What do you mean by something called linear? What is the motivation for this subject? The motivation is the following. Okay, let's go back to class 9. Two x plus y equal to 3, x plus y equal to 4. Okay, so okay, so what is the solution of this system? I don't. Okay, what is the solution of this system? What do you mean by what do first of all what do we mean by the solution of this system?
The values of x and y will satisfy the equations.
Yes. And what are the values of x and y that satisfies this equation?
X equal to minus 1 and y equal to 5.
X equal to -1 and y equal to 5. Okay. Yes. Are there any? Is this is this a unique solution or does there exist any other solution? How do we find the solution? Someone give us a solution. How do you know that this is a solution?
By substituting the second equation in the first.
Okay, so you are using the substitution method. Okay, okay. So we have two questions now. Is the solution unique? First of all, and what is the name of such system? Usually, what do we call this system? What is the name of such system? You know what is What is system of linear equations? What is do you know something called system of linear equations? Please answer. Do you know something called system of linear equation? You have seen it in class 12. Okay, what these two equations geometrically mean? What these two equations geometrically represent?
Two straight lines.
Sorry?
Two straight lines.
Okay, two straight lines. Okay, so in R2 you have two straight lines. So what are the condition? What are the possibilities of two straight line?
Either there is infinitely many solutions or unique solution or no solution.
When there is a unique solution,
When the lines intersect at only one point.
can a line can two straight line intersect in two different point?
No.
Can you prove it geometrically?
Okay.
It is a bit non-trivial. Okay. So basically these two equation in R2 represent two straight lines. So we have three possibilities. Either these two straight line can intersect in one point. Okay, so what is the what is the condition of these two straight line? Okay, what is the condition that this system of linear equation has infinitely many solution?
A1 by A2 equals to B1 by B2
No, no, no,
equals
no.
to C1 by C2.
But why this? But why this condition comes? You are saying something, but why this is true? Think geometrically. These two equation is given by some straight line in R2. So either they will intersect at one point, or they will so two straight line may intersect at one point, may not intersect at any point, or what are the possibilities? And this may happen they are parallel to each other, or this one
They can be stick to each other.
and this one they are on the each other. No, those two, then you have infinitely many solution. They are they are intersect each other infinitely many times, that they are intersecting in this point, this point, this point, this point, this point, and so on. So having an infinitely many solution means they are basically same straight line. They are basically the same straight line. So the system of linear equation will have a unique solution if this holds. In this case, this really holds. We'll have no solution in this case. Two parallel straight line never intersect each other, and or infinitely many solution. In that case, the straight lines, these two straight lines are really same straight lines. These three are cases. So this is basically a straight line. This 2x plus y equal to 3 or ax plus by equal to c. So basically this represent a straight line in R2. So that's why they are called linear. Okay. So these are called linear equations, and if you have a bunch of them, you call the system of linear equation. I have two linear equation. I want to find the solution. So this is known as system of linear equation. You have bunch of linear equation in your head. So this is the whole collection is called system of linear equation. And the idea is to find the system of linear equation. Okay, so forget about this. 2x plus y equal to 3. What is the solution of this equation? This is the linear equation. What is the solution of this equation? So since you have done a bit of group theory, you should know what is something called Diophantine equation. Yes. A Greek mathematician Diophantus, probably the earliest ones to work with those linear equations. Basically, Diophantus wants to find first. Okay, let's say Diophantus wants to find the solution of such linear equations in Z. So I want to find x and y from Z such that satisfies this equation. So this is something called Diophantus equation, and the solution of this Diophantus equation means I want to find the solution in Z. So this is not by Diophantus. Diophantus want to find the solution in rational number, and the solution in rational number is easy. So he did not consider this. This directly go into the quadratic polynomial. Say ax square plus bxy plus cy square equal to d. So Diophantus want to find this solution of this quadratic equation in integer. In rational number. But later someone wrote a book on Diophantus and his work, and then he included the system of linear equation and the solution in integer. So basically we call them the system of the Diophantus equation if the coefficients are coming from integer, and if we want to find a solution in integer. Basically this is purely number theoretic stuff. You must know what is the solution of this Diophantus linear equation, and when the solution in integer exists, and if the coefficient of the GCD is 1, then the solution is exist, or the coefficient of the GCD divide the constant term, then the solution exists in integer. And this is not the unique solution, of course. This is given by a one parameter family of solutions. So basically if you have basically this is a straight line. So what is that? 2 by 3 and 1 by 3. So you have to say they are the solution. Basically you find one solution, and you are varying t from real number to find the rest of the solution. So this is a one parameter family of solution, and solution is not unique, of course. So this is something called Diophantus solution. And if you have a bunch of these linear equations, we call them the system of linear equation. More formally, suppose we have a11 x1 plus dot a1 a1 in xn equal to y1, a m1 x1 plus dot 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 plus a mn xn equal to yn. More suppose we have this, then let's call it star. Then star is called a system of linear equation of n unknown and m equation. Okay, this is m. See, you have m many equations and n many unknown number x1, x2, xn. You want to find for which x1, x2, xn all these m many equation have the solution y1, y2, yn. You want to find such a solution, but the question is why we are interested to find the solutions. There may be several reasons. The earliest work, as I say, the diaphantists want to find a solution in rational number or in integer. Suppose you want to generalize it. Now you are saying, okay, I have to say linear equation. I want to say I have to linear equation. That means I have to straight line. I want to see whether this straight line intersect or they are parallel to each other or they are the same straight line. So geometrically saying, when I have say m equations and n unknown, basically in some Rn, R1 cross R2 cross Rn, there are m many surfaces. Okay, not surfaces, m many planes, and I want to see that where these m many planes intersect, or they don't intersect each other, or they are parallel to each other, or there are several cases. Suppose in R3 you have two different planes. It may happen that these two different planes may intersect at the single point. It may happen, or they intersect at a straight line. Suppose you have two planes, they may intersect at a straight line, or they may intersect at a point, or they don't intersect, they are parallel to each other. So the geometrical interpretation is that you want to see whether these m many surfaces in Rn have solutions, or I mean they are intersecting each other, or they are parallel to each other, or how many of them are intersecting each other, how many of them are not, how many of them are parallel to each other, all these things. So you may take it as a motivation for this subject, that I want to find the system of linear equations, and hence the term called linear algebra comes. We want to develop some algebraic stuff so that I want to find the solution of such system of linear equation, and this is quite really helpful for us, because in everyday life we do such things. We have some equation we want to solve and we want to see, then we want to interpret in our terms. Okay, what is the interpretation? For example, you all of you have seen the something called linear programming problem, LPP. So in LPP, what we are doing, we have some constraint and we want to maximize or minimize some function. So I have some different constraints. So basically I want to solve these constraints so that I find some values, and then I want to say, okay, so for this value I have the so this function maximizes or this function minimizes. So solving system of linear equations has really a importance in our daily life, solving LPP problem and many others. Okay, let's start. Usually we take Aij just a minute. K of field YA for all Ij. A solution, what to say, T1 T2 Tn. Everybody knows what do you mean by Kn. Element T1 T2 element is said to be a solution of star if T1 Tn T1 Tn is a solution of the system if I don't know.